Hey there, and welcome. We are about to jump into a massive cosmic detective story. We're going to follow some totally invisible clues to try and uncover one of the universe's biggest secrets, evidence for something that makes up 85% of all the matter out there, but is completely, totally invisible. Let's get right into it.
So, it all kicks off with a really simple question. When you see a picture of a spiral galaxy, it's just beautiful, right? Billions of stars swirling in this incredible cosmic dance. But what's actually keeping them all together? The easy answer is gravity, of course. But as you're about to see, that simple answer, well, it's not even close to being enough.
So our mystery really gets going with astronomers like the brilliant Vera Rubin. They started measuring how fast stars and other galaxies were moving, and they fully expected the stars on the outside to be moving slower, kind of like how Pluto moves way slower than Mercury in our own solar system. But that is not what they found. Instead, the outer stars were moving at insane speeds, so fast that the gravity from all the stars and gas we could see just wasn't strong enough to hold on. They should have been flung off into deep space ages ago.
And this bizarre observation gets plotted on something called a galaxy rotation curve. It's basically a graph of star speed versus distance from the center. The dotted line shows what we expected to see, speeds dropping off the further out you go. But the solid line shows what we actually saw. The speeds just stay flat. They stay incredibly high. This flat curve was the first giant red flag that something was fundamentally missing from our picture of the universe.
The only logical conclusion was, frankly, mind-boggling. For those superfast outer stars to stay in their orbits, there had to be a ton of extra gravity holding them in. And since mass is what creates gravity, that meant there had to be a gigantic halo of invisible stuff surrounding the entire galaxy, an enormous amount of unseen mass.
But okay, one strange observation, as weird as it is, doesn't make a case. But that's the thing, this was just the first clue. As other scientists started looking deeper, using completely different techniques, the evidence for this invisible culprit just began to pile up.
Our next big clue comes to us from Einstein himself. His theory of general relativity tells us that anything with mass actually warps the fabric of spacetime, and that bend can deflect light. It's called gravitational lensing. And it's an amazing tool because it lets us weigh huge things like galaxy clusters just by seeing how much they distort the light from galaxies sitting behind them. It reveals the total mass, not just the stuff we can see.
And what did they find? The results were just staggering. The amount of light bending they saw was way more than all the visible galaxies and gas could ever account for. As the researchers studying this put it, they were finding direct evidence of two large-scale dark matter clumps. They weren't just guessing it was there. They were literally mapping out its gravitational shadow.
All right, our third piece of evidence comes from the universe's own baby picture, the cosmic microwave background, or the CMB. This is the ancient light from just after the Big Bang, and it fills the entire sky. And the tiny little patterns in this light are like a blueprint. They are the seeds that eventually grew into all the galaxies and galaxy clusters we see today.
Now here's where it gets really powerful. Scientists can take that blueprint from the CMB and run these incredibly complex computer simulations to see if they can grow a universe that looks like ours. And they found there is only one way, and I mean the only way, to get the simulation to match the universe we actually live in. And that's if you add a huge amount of cold, invisible dark matter right from the very beginning. If you don't, the models fail completely.
So let's just step back and look at the case file. We have weirdly fast galaxies. We have gravity from gravitational lensing that's way too strong. And we have the blueprint of the early universe. Three totally independent lines of evidence. And here's the kicker. They all point to the exact same conclusion, that about 85% of all the matter in our universe is missing. So with this much evidence from so many different angles, the investigation really starts to shift. The question isn't if there's something missing anymore. The question becomes, what is it? And the leading suspect is some new kind of matter, some new particle that doesn't interact with light at all, which, is why we call it dark. But, in any good investigation, you have to consider the alternatives. What if we're all just completely wrong? What if there isn't any missing matter? What if our understanding of gravity itself is the problem? Maybe Newton and Einstein's theories just don't work the same way over these gigantic cosmic distances, creating an illusion of missing mass. Well, to test that, nature gave us the perfect experiment. Meet the bullet cluster. This thing is the aftermath of a cosmic collision on a scale that's almost impossible to imagine.
two entire clusters of galaxies that smashed into each other and passed right through. And this cosmic car crash was the perfect test to see if we're dealing with dark matter or with a new theory of gravity.
So let's break down what happened. When these two clusters collided, all the normal matter, mostly clouds of superheated gas, smashed into each other and slowed down, kind of like a cosmic traffic jam. But the dark matter, since it barely interacts with anything, should have just sailed right on through without slowing down at all. So you get a separation. The question is, where did the gravity end up? With the slow gas or with the stuff that passed through?
And this is the smoking gun. When astronomers measured where the center of gravity was, they found it wasn't with the hot gas, where all the normal matter was. It was out ahead, exactly where the dark matter should be. And that is a huge deal. Why? Because you can't separate gravity from the matter creating it. This collision physically separated the stuff from its gravitational effect, proving that the missing mass is a real physical substance, not just some weird quirk in the laws of gravity.
Okay, so the evidence is pretty overwhelming, right? We have multiple clues, and we've even seen this stuff get separated from normal matter. Now, this is usually where the story about dark matter ends, but honestly, this is where it gets so much deeper and, frankly, way more interesting.
So, does that mean the case is closed? We found our mystery substance, we just need to figure out exactly what particle it is, and we're done? Is that it?
Not even close. Because the existence of dark matter isn't just the answer to an astronomy puzzle. It's actually a giant, flashing arrow pointing to a much more fundamental question about the very rules of our reality.
The real question dark matter forces us to ask is this: is our standard model of physics complete? I mean, this model is our crowning achievement. It describes every known particle and force in the universe with incredible precision. And yet there is literally no room in it for dark matter. The real takeaway isn't just dark matter is real. It's that our most fundamental theory of everything is incomplete.
And that right there is the real verdict from our whole investigation. The hunt for dark matter isn't just about finding some weird new particle floating around in space. It's about finding the key that unlocks the next chapter of physics itself.
And here's the wildest part. Particle physicists, the people who have nothing to do with galaxies or cosmology, they've actually known for decades that the standard model isn't the final word. For their own reasons, they have been predicting that new, undiscovered particles must exist.
Yeah, for a long time now, particle physicists have had their own list of problems. They need new particles to solve things like why the Higgs boson has the mass it does, or to make bigger ideas like supersymmetry work out. And get this, even most of the alternative gravity theories we talked about, they often end up needing new kinds of particles to make their math work too. So nearly every path forward, from every direction, points to the fact that our current list of particles is just the beginning.
And that is the grand finale. This is the big takeaway. You have astronomers looking out into the cosmos, and you have particle physicists looking into the quantum realm, and they have both arrived at the exact same conclusion from completely different directions. Our universe requires new physics. Our list of particles is incomplete, and dark matter isn't just some weird patch to fix a problem with galaxies. It is the single best, observationally proven candidate for the new physics that we already knew we were looking for.
And so that brings us to the final thought. The discovery that dark matter exists is, well, it's humbling. It tells us that every single thing we have ever seen or touched, every star, every planet, every person, is made of just 15% of the stuff out there. Which leaves us with one last, massive question to chew on. If we were missing something this huge, right in front of our faces, for this long, what else are we missing?